I'm not going to say much about the test, especially the multiple choice section. In this document that I'm projecting, it will be available under doc sharing later. So I kind of want to skip on to that first problem. And I kind of lose track of who got it, who didn't get it. But I think the first question here, a lot of students didn't get. Basically, you were supposed to use this right here to answer those questions. And the fact that, that the molar concentration of, for instance, can you see we have R and Q that are decreasing, and we have P that's increasing, so that's the product. So can you see where Q is decreasing twice as fast as R? And actually, if you look at the rate of increase of P, it's equal to the rate of increase of Q. So we have some stoichiometry going on there. Okay. So the best way to describe that, you can either go P plus, you can either go Q plus 1/2 of P goes to form, sorry, Q plus 1/2 of R goes to form P, or like I did, 2Q plus P goes to form 2P. 2Q plus R goes to form 2P. And then these actually, this one right here, B, it said go ahead and find the curve for Q. Look at that curve between 2 and 5 minutes. Come up with the change in molar concentration and divide it by the time to get the rate. So that's the rate of change of Q. Now you had to, in order to get C right, you had to get this right. Because according to this, we need to, if we're tracking the rate of change of Q, then we need to multiply by -1/2 to get the real rate. And that's what I've done here. Because Q has a coefficient of 2 in front of it, and it's a reactant. So the rate is kind of related to B, so C is related to B. And then the D actually just goes for the product in a different interval. So again, you look at the change in the molar concentration over time. Let's see. Then we go to this one, and you can do by inspection. You can actually do get to the reaction order of the CHCl3. If you compare trials 1 and 2, the fact that you double the concentration of CHCl3 and you see actually the rate double, that means that it must be first order with regard to that reactant. The only way to get the reaction order of Cl2 is mathematically or algebraically. I've done it down there in the answer key. And it's weird because it comes up with reaction order of 0.5. So the overall, you add them together. So now when I was grading it, if you got a different reaction orders, but add them together to get the overall reaction order, I took that into account. So for the last one, if you want to knock out K, you just have to pick any trial and substitute in the rate law expression and solve for K. This one was where you had these 3 different graphs and you had to see which one was straight. And so actually the first order test is straight, so that must mean it's first order. And in that case, then the slope is equal to -K. And you had to actually, in order to answer the question, you had to come up with a slope of that line. I chose points at 100 seconds and 600 seconds. Now, in this case, we don't undo the natural log, which is what we plotted over here. We simply take the difference in those y values divided by the difference in time to get to the slope. And so the slope is equal to -K, so there's K. Then this one, it told it was first order. So if it's first order, we're kind of using this sort of situation, integrated time concentration equation. And we also have to use the half-life equation. They give us the half-life is 17.0 minutes, so we can actually use that half-life right here to get to the rate law constant K. The catch here then was that when you solve for this quantity A over A0, that is the fraction of A remaining, and over here you're supposed to have what will have reacted by that time, 20.0 minutes. So a lot of times students were getting this right but not continuing on to getting the amount that reacted. And then this one was also, oh, nope, this one was second order. You can tell it's second order here. So since it's second order, we know we need to use this integrated time concentration equation. K was given, and we simply substitute in. It looks a little messy. And then this one was Arrhenius plot. So you needed to knock out a few more columns convert temperature from Celsius to Kelvin, and then take the inverse of that temperature, and that's going to go along the x-axis. Along the y-axis, we take the natural log of rate log constant, and put those on there, and that is an Arrhenius equation. And then down here, we're supposed to come up with the activation energy, and the slope of the Arrhenius plot. So that's change in the natural log of K divided by the inverse change in the inverse temperature. So we go ahead and come up with the slope, and we know that's related to activation energy. Slope is equal to negative EA over RT. So we can solve for the EA, and I got about 92 kilojoules per mole. And then this one, you're supposed to say how many mechanisms. There's 2 mechanisms because there's 2 humps. It's actually exothermic because there's less energy at the end than there is at the beginning. Energy is released. The activation energy of the rate determining step, that would be the activation energy of the highest activation energy. So that actually is 1, or excuse me, that's 4 right there. The overall enthalpy change of the reaction, that would be 8. The enthalpy change for the first elementary step, 3. You can kind of see those. Then number 9 was kind of leading up to number 10. So you were supposed to come up with the overall reaction of interest, adding those 2 elementary steps. Of course, CL is an intermediate. The slow elementary step is the rate determining step. It happens to be the first. And then from that, we can come up with the proposed rate law expression from that slow step. And then actually, when we say write the rate law expression for the overall reaction based upon the slow step, it would be the same. So D and E are the same. Very common mistake was to go back up to what you came up with up here and use molecularity, which you cannot use unless it's an elementary step, to come up with a reaction order of 2, but it's really 1. And then my last page actually is on a separate document, so when I upload it, there'll be 2 documents. This one to come up with the overall, given these 3 elementary steps, this is the overall reaction of interest. There are 2 intermediates, H and HCO. The rate law expression, again, we turn to the slow step. That would be the second step. The thing about that is we have an intermediate, which is H, and so we need to get rid of that. We can get rid of that if we turn to the first elementary step, which is fast to equilibrium. So the rate in the forward direction is equal to the rate in the reverse direction. Solving for H, we end up with K1 over K minus 1 times H2, molar concentration H2, which is a real substance, raised to the 1/2 power. So if we substitute that quantity in for this up here that we got in C, then we end up with rate is equal to K molar concentration of H2 raised to the 1/2 power times the molar concentration of CO. Where actually that K has this sort of information going on in the background with regard to the first and second elementary steps. So, like I said, that will be posted later. In the meantime, we need to go on with